Welcome students. Today's class we will be starting off in learning linear differential equations. Now the first and foremost thing that you will have to know is the definition. So let me write that down. Differential equation is said to be linear if the dependent variable and its differential coefficients occur only in the first degree and not, this is very important, and not multiplied together. Now what exactly does it mean? Now the meaning is we are looking at a system in this fashion: dy over dx positive p times y is equal to q, where p comma q are the functions of x. Now when we talk about dependent variable, let me write that down, dependent variable, and there is also what is called as independent variable. Now if I were to take dy over dx, the dependent variable is y and the independent variable is x. So have that in mind. So that means what they are saying is it's purely acceptable if you have something like this, say d squared y over dx squared positive something, say p times y is equal to some q. Now this has an order and it has a degree. Now the degree should always be 1. So this is a differential equation. Now if someone were to ask you, say, what can you say about this one? Say y times dy over dx positive p times, say, y squared is equal to q. Is this a differential equation? The answer is no. No. Why? From the definition, you cannot have y multiplied with dy over dx. Have it in mind. On the contrary, if someone were to ask you x times dy over dx positive some p times y is equal to q, is this a differential equation? Yes, because x is an independent variable. Now we are going to look into some illustrations and we will further our studies with sufficient examples. Okay, the first example is, say you got something like this, say y squared dy over dx is equal to x to the power of 3y positive x to the power of 5. The question is this a differential equation or is this a linear differential equation? Yes or no? Can we say that this is a linear differential equation? True or false? Tell me. The answer is false. This is not a linear differential equation for the given fact that you got y squared being multiplied with dy over dx. So this is false. So let me go on and give you example number 2. Say you got, say, x to the power of 5. Say dy over dx is equal to 2 times x to the power of 3y negative 1 5. Is this a linear differential equation? Can you say true or false? What would you say? Of course, the answer is true. I can always have x to the power of 5 multiplied with dy over dx. That isn't the issue. But I cannot have y squared multiplied with dy over dx. This is a very big issue. So have that in mind. Now, coming to example number 3. Say for example you got something like this. Say x times d squared y over dx squared negative x to the power of 3 dy over dx is equal to 5 times y positive some 81. Is this LDE, a linear differential equation? Of course, the answer is going to be true. Okay, it doesn't matter if I have x or x cubed, but I should not have any y term. So having mentioned this, now you might be wondering what sort of linear differential equation this is. So this is linear, let me write that down, linear differential equation of order equal to 2, just to give you some information on this particular example. Other examples are straightforward and I'm sure that you are well aware of it. So let us move on. Students, we are going to learn the standard form. standard form of linear differential equation. So what exactly is the standard form? Now have it in mind. This standard form is also called as Leibniz, Leibnitz. Leibniz is one of the inventors of calculus. So this is also called as Leibniz linear equation. So that's important. Some details of these great people are very critical in understanding the subject, because people like Leibniz, Newton, Euler, Fermat, they're all great people who have dedicated their entire life in the discovery of the concepts of mathematics. In fact, there are scores of people who are worthy of mention, but apparently we will learn about them as we progress in this particular journey. So Leibniz, as I mentioned to you, Leibniz and Newton, Sir Newton and Sir Leibniz, both of them are credited with the invention of calculus. Well, most of the concepts of calculus that we are seeing is from Leibniz, right? So this standard form of linear differential equation is also known as Leibniz linear equation. Now the form, it is important that we understand the form of the LDE. Now what is the form of LDE? So how does the LDE looks? It is given to be as dy over dx positive p times y is equal to q. As I mentioned to you in the very beginning, where p comma q are functions, okay, are functions of x. Now the question is, how are we going to solve it? Solving is very critical, right? This is a system and we have to solve them. Solving it is very critical. Now why is it critical? Only when we solve it, we know the answer. Just as in life, every complex situation or a complex case or a complex scenario is associated with a problem, right? And just as in life, we need solutions to them, right? And the mathematics develops our mind and our ability to think to achieve such solutions. So imagine that we have a system, okay? This system is connected with certain real life problem and it has a representation in this fashion. The question comes, how are we going to solve it? Now to solve this, what we have to do is we will have to multiply. Let me just take this as 1. We will have to multiply 1 by e raised to the power of integral p dx. So this is a very important component. So we will have to multiply 1 by this. So what happens when we do that? So I get, let me write that down, dy over dx multiplied with e raised to the power of integral p dx positive. I'm going to write this as y times of e raised to the power of integral p dx times, I got a p there, so I'm writing the p like this, is equal to, now I got a q there and then I will follow it as e raised to the power of integral p dx. So this is what we have got. Now clearly, if you were to observe this, this is nothing but UV form. So I can clearly rewrite this as d over dx of, I'm going to represent this as y times e raised to the power of integral p dx. This is equal to q times e raised to the power of integral p dx. Now let me just show you what happens with this. So I'm going to use this space here. Now I'm differentiating this term, right? So if you have d of uv, what is the differentiation? U times v dash positive v times u dash, right? So this is going to be y times, you're going to differentiate e raised to the power of integral p dx. So now if you were to differentiate a quantity like this, what would happen to this quantity? This quantity would actually be as retained, because this is going to be exactly e raised to the power of integral p dx. So I just place p there. Positive, I need to now differentiate y term. So that is going to be e raised to the power of integral p dx times dy over dx. So this is exactly what we've got, right? dy over dx times e raised to the power of integral p dx positive y times, so differential of this, so when we differentiate this, this is going to be resulting in e raised to the power of whatever quantity we've got times the quantity that is acting as a coefficient. So we got to multiply that. So this is what we have got now. So having got this, what I'm going to do, I'm going to cross multiply. If I were to cross multiply, this is going to be d of y times e raised to the power of integral p dx is equal to q times e raised to the power of integral p times dx times dx. So this is what we've got. Now I want to get rid of this d. So what I wish to do, I wish to integrate both sides. So this integral and the d will get neutralized. So thereby giving me y times e raised to the power of integral p dx is equal to integral q times e raised to the power of integral p dx times dx. Since I am integrating, there will be a presence of an arbitrary constant. So the solution of a linear differential equation is this. And understanding this is of much importance. So we will move on to do other related questions. Students, we are expected to solve this linear differential equation, and foremost thing is we would love to convert this into standard linear differential equation. So what is that? Which is nothing but dy over dx positive p times y is equal to q, where p comma q are functions of x, right? So let us see if we can get the problem in this fashion. So first what I would do is, if I were to take this as 1, therefore I can rewrite 1 as x positive 1 times dy over dx negative y is equal to e raised to the power of 3x times x positive 1 raised to the power of 2. I wanted to have q, this is my q term, because q is a function of x. And now I need to have p times y, and there shouldn't be any coefficient with dy over dx. So what I will do is divide by x positive 1 throughout. So if I were to do this, I would get dy over dx negative y times 1 over x positive 1 is equal to e raised to the power of 3x. Now x positive 1 raised to the power of 2 divided by x positive 1. That is going to give me x positive 1, right? So now this is exactly in this standard form. So where p is equal to negative 1 over x positive 1. And my q is e raised to the power of 3x times x positive 1. So this is fair enough. Now the solution, excuse me, the solution for the LDE. What is the solution for the LDE? We achieved a solution as y times e raised to the power of, we have already deduced the solution. Integral p dx is equal to integral q times e raised to the power of integral p dx, of course, times dx positive c. Now this is the integrating factor, right? So we call this quantity as integrating factor. So we write it as integrating factor, and we abbreviate it as IF. Okay. So we will have to obtain the integrating factor. So how are we going to obtain the integrating factor? This is nothing but e raised to the power of integral p dx. This is the integrating factor, which is nothing but e raised to the power of integral. My p is negative 1 over x positive 1. So I'm going to write it as dx over x positive 1. So this is nothing but e raised to the power of integral of this. What would you get if you were to integrate this particular quantity? This is going to give me ln of x positive 1 with a negative sign. I know that there is a law. So what is the logarithmic law? Let me just write that down. A times ln b is equal to ln of b over a. This is the property I will be using. So I can move this over here. So this is going to be e raised to the power of ln of x positive 1 raised to the power of negative 1. So let it be like this. Now you can see that you got e here and you have a natural logarithm here. So both of them will get neutralized, giving me x positive 1 raised to the power of negative 1. I can rewrite that as 1 over x positive 1. This is my integrating factor. So fair enough. So now we will have to calculate. So let us consider this quantity. So we will have to integrate this. Consider integral q times e raised to the power of integral p dx, which is nothing but integral. My q, I have already taken my q as e raised to the power of 3x times x positive 1 times e raised to the power of integral p dx. What is that? E raised to the power of integral p dx is nothing but 1 over x positive 1. Of course there is a dx here. We should always have that. Without that the integration cannot be performed. So clearly what happens here, x positive 1 can be cancelled, giving me integral e raised to the power of 3x times dx, which is nothing but e raised to the power of 3x. Coefficient of x is 3 and we have to place the arbitrary constant c. So now the solution. So we call it as general solution, or depends on whatever you wanted to specify. Either you can say general solution or solution. So what is the solution? We know that integral this is on the right hand side, integral q times e raised to the power of integral p dx positive c. On the left hand side it's going to be y times e raised to the power of integral p dx. So this is the solution. So according to this, now y times e raised to the power of integral p dx, e raised to the power of integral p dx is going to be y over, this is actually 1 over x positive 1, is equal to this quantity. We have already evaluated this quantity to be as e raised to the power of 3x divided by 3 positive arbitrary constant c. So this is the solution that we have got. If you want to have only y here, you can always write this as y is equal to e raised to the power of 3x divided by 3 positive c times, you can cross multiply, so it's going to be x positive 1. So this can be taken to be the solution. If you're happy about this, there is no harm even to stop at this particular point. If you are given an MCQ and if you can only spot this to be the choice, then you will have to bring it all the way to here. So we'll move on to the next question, students. Students, we are given a beautiful question. Solve is a linear differential equation, and the question is e raised to the power of negative 2 times root of x divided by root of x negative y times root of x times dx over dy is equal to 1. Now this is solvable owing to the fact that we got dx over dy, and that is an added advantage. So what I wish to do is I would like to move dx over dy down. So this would mean I now have e raised to the power of negative 2 times root of x divided by root of x negative y times root of x is equal to 1 over dx over dy. Now I flip this dx over dy. So what do I get? I get e raised to the power of negative 2 times root of x divided by root of x negative y divided by root of x is equal to dy over dx. So this is what I've got now. Now I need to bring it in the required form. The required standard linear differential equation form is, so what is the required linear differential equation form? Dy over dx positive p times y is equal to q, where p comma q are functions of x, right? So I need to get that. So dy over dx is going to be there. I'm going to push y over root x to the other side. So that would mean I got positive y over root of x, and I'm going to retain e raised to the power of negative 2 times root of x divided by root of x. Now this is clearly in the standard form. So I can specify here where my p is 1 over root of x. So that's my p, and my q is e raised to the power of negative 2 times root of x divided by root of x. Now we need to get the integrating factor. So what is the integrating factor? Which is nothing but e raised to the power of integral p dx. This is what is the integrating factor. From here I can say this is nothing but e raised to the power of integral. My p is 1 over root of x times dx. Right? This is what I've got. So what I wish to do is I will first consider integral dx divided by root of x. So this integration, this is rewritten as dx divided by x raised to the power of 1 over 2, which is nothing but x raised to the power of negative 1 over 2 times dx, which is nothing but x raised to the power of negative 1 over 2 positive 1 divided by negative 1 over 2 positive 1, which is x raised to the power of positive 1 over 2 divided by 1 over 2, which is nothing but 2 times root of x. Of course, there is a positive constant c. I don't have to specify it right now. So hence the integrating factor is e raised to the power of integral p dx is equal to, in place of integral p dx, I will have to specify 2 times root of x. Probably I will just say consider integral p dx. Okay. So I've got this integrating factor. So now I will have to consider integral q times e raised to the power of integral p dx times dx. Now what is my q? My q is e raised to the power of negative 2 times root of x divided by root of x. What is my e raised to the power of integral p dx? This is going to be e raised to the power of 2 times root of x times dx. Now do you see what I see? You have e raised to the power of negative 2 times root of x, and you got e raised to the power of positive 2 times root of x. So we got a favorable outcome. So I can simply cancel these two. If I were to cancel these two, I would get dx divided by root of x. Now this is going to be, this is actually x raised to the power of half, right? So this is going to be x raised to the power of negative half times dx. If I were to integrate this, I would get the same thing, 2 times root of x. This is what I'm going to get. So I can directly substitute that value, 2 times root of x. So now the solution part comes. So therefore the solution, so all of these things are working. So the solution is y times e raised to the power of integral p dx. That's a solution, right? So let me show you the solution, general solution that we are looking for. This is the general solution that we are looking for. So I will just substitute it, probably because of the lack of space. So y times e raised to the power of integral p dx. Where is our integrating factor is going to be y times e raised to the power of 2 times root of x is equal to this quantity. This quantity is nothing but 2 times root of x. So just substitute that 2 times root of x. Finally, we will have to place the arbitrary constant. That is very much important. So without the arbitrary constant, the solution is not correct. Of course, there may be people who might argue, oh, it's okay, we can just simply drop this. But no, we cannot drop it. Arbitrary constants are very, very important. So we need to place it. Okay, so this is the solution for this particular beautiful question. So we will move on to the next question. Students, we are given a question: 3 times x of 1 negative x squared times y squared times dy over dx positive 2 times x squared negative 1 times y raised to the power of 3 is equal to ax cubed. Now in this original fashion, if someone were to ask you, is this LDE, a linear differential equation, obviously your answer would be no. Why? Because we got y squared as a product multiple with the differential coefficient, right? So this is the exact definition that we started off with. Now we should not lose heart. In other words, we shouldn't outrightly condemn this system and ignore it and move on. We shouldn't do that. So what we have to do here is to try some certain principles in manipulation in changing this. So that's exactly what we're going to do. So what I will do is I will say let say y cube be equal to some z. I'm going to take this. Next I'm going to be differentiating this, okay, with respect to x. So this is going to be 3 times y squared times dy over dx is equal to dz over dx. So this is what I've got. So now wherever I have 3 times y squared dy over dx, I can substitute dz over dx. So if I were to take this as 1, I can rewrite 1 to be as, foremost, let me just bring it in this fashion. So this is x times 1 negative x squared times 3 times y squared times dy over dx positive 2 times x squared negative 1 times y cubed is equal to a times x cubed. Now as I mentioned to you, you got 3 times y squared dy over dx, so I can substitute. So this is going to be x times 1 negative x squared. This entire thing which you see here can be substituted with dz over dx positive. This is going to be 2x squared negative 1. Now y cube, I am taking it as z, so this is going to be a times x cubed. Now what I wish to do, I would want to get rid of this entire coefficient. So what I will do is I will be doing, in other words, I will be dividing throughout by x times 1 negative x squared. So when I perform the division, I would get dz over dx positive 2 times x squared negative 1 times z divided by x negative 1 negative x squared is equal to a times x cubed divided by x times 1 negative x squared. This is what I've got. So now the question comes here is the integrating factor. So this is clearly of the form, this is of the form dy over dx positive p times y is equal to q, right, where p and q are functions of x. So clearly I can see that, so if I were to take this as 2, so I can state that from 2 my p is 2 times x squared negative 1 divided by x times 1 negative x squared. So therefore the integrating factor, so what is the integrating factor? E raised to the power of integral p dx, which is equal to e raised to the power of integral 2 times x squared negative 1 divided by x times 1 negative x squared times dx. So I need to integrate this. So to have this integrated, we need to adopt some techniques of partial fraction. So we can do that. So I'm just going to take this first and I will integrate this. So what I'm going to do is I'm going to be rewriting, of course you got to have a dx there. I'm going to be rewriting this as 2x squared negative 1 times dx divided by x times 1 negative x squared. I can write it as 1 negative x times 1 positive x. Now I need to use partial fractions as I just mentioned to you. So I would just say consider 2 times x squared negative 1 divided by x times 1 negative x times 1 positive x, which can be rewritten as a over x positive b over 1 negative x positive c over 1 positive x. If I cross multiply, this is going to be a times of 1 negative x times 1 positive x positive b times of x times 1 positive x positive c times of x times 1 negative x. On the left hand side you get 2x squared negative 1. Now if I were to take x is equal to 1, this goes off, the first term goes off, x is equal to 1. If I were to take x is equal to 1, this one also goes off. So I am left with b of 1 times 1 positive 1, which is going to give me 2 times b. On the left hand side, x is equal to 1, 2 minus 1. So I would have the value of b is 1 over 2. Okay. Now next, let me use the space over here. I'm going to take x is equal to negative 1. If I were to take negative 1, this goes off. X is equal to negative 1, b goes off, a goes off, negative 1, that's going to be positive. So it's going to be 2c, but there's going to be a negative 1, so it's going to be negative 2 times c. Negative 1, this is going to be positive because of the presence of the square, so this is going to give me c is equal to negative 1 over 2. Okay, that's fine. So we got a, I would say we got b and c, we need to get a. So what I'm going to do now, I'm going to take x to be equal to 0. If I take x is equal to 0, this is down, this is down. This is going to give me 0, positive 1, and that's going to give me a times of 1, 1. So that's going to be fine. Over here, this is going to be 0, and I get minus 1. So therefore the value of a is negative 1. This is what I've got. Now what I can do is, hence, from all these partial fractions, what I can write is integral 2 times of x squared negative 1 times the dx divided by x times of 1 negative x times 1 positive x is rewritten as negative 1 over x positive 1 over 2 times 1 negative x, and my c is negative, so it's going to be 1 over 2 times 1 positive x times dx, right? So this is going to be integral negative 1 times dx over x positive 1 over times dx over 1 negative x negative 1 over 2 times integral dx over 1 positive x. Now this is going to give me negative ln x positive 1 over 2 times. This is going to give me ln of 1 negative x. Of course there is a negative sign with x, so it's going to be negative 1 there, followed by negative 1 over 2 times ln of 1 positive x. Now I want to rewrite it one more time just to avoid any confusion. So negative ln x, negative 1 over 2 ln of 1 negative x, negative 1 over 2 ln of 1 positive x. Now I got a negative negative, so I'm going to take the negative sign out. So if I were to take a negative sign out, this is going to be ln of 1 positive x, I'm writing this term first, followed by positive ln of 1 negative x. So these two can be added. Why it can be added? Because ln a plus ln b is equal to ln of a times b. We know this property. So this is going to be negative ln x negative 1 over 2 times ln of 1 positive x times 1 negative x. That's going to be 1 negative x squared. So probably I can, first I want to take this half over here. So if you want to take the half, it's up to you. If you can do that, but before you can, okay, let me just do that. So it's going to be negative ln of x. So negative is going to be ln of 1 negative x squared. Okay, 1 negative x squared raised to the power of, this half can be rewritten. This can be further rewritten as negative ln of x, negative ln of 1 negative x squared raised to the power of half. That's going to be root of 1 negative x squared. So that's what we have got. We got two negatives here. I'm going to take a negative sign out. So it's going to be ln of x positive ln of root of 1 negative x squared. Ln a plus ln b, that's going to be ln of x times root of 1 negative x squared. So I've got a quantity. What is all this about? This is all about finding the integrating factor. In fact, it is actually not even integrating factor. All I have done is to find e raised to the power of it's just integral p dx. It is not even e raised to the power of integral p dx. It is just integral p dx. Now we have achieved all this. So now we have to obtain the integral factor. So let me just write it down. So therefore the integrating factor is e raised to the power of integral p dx, which is equal to e raised to the power of negative ln of x times root of 1 negative x squared. So this is what I've got. Now I can throw this negative sign over here, okay, to the whole of this. So that's going to be e raised to the power of ln of x times root of 1 negative x squared. This is raised to the power of negative 1. E and ln, they get neutralized. So that is going to give me x times root of 1 negative x squared raised to the power of negative 1. I can rewrite this by bringing it down. So that's going to be if is equal to 1 over x times root of 1 negative x squared. So this is what is my integrating factor. Now we have got the integrating factor, but the question now is we will have to obtain the solution. So in fact, before we can obtain the solution, we will have to find out the integration of, now consider integral of q times e raised to the power of integral p dx times dx. We have to do this, right? Of course, this is achievable, and the only thing is that we will have to get our q. So from the question, we know that the q is, we have got the q to be as ax cubed divided by x negative x cubed. This is our q. So that is exactly what I have just written here for my q. So I have to take this and substitute here. So this is going to be a times x cubed divided by x negative x cubed times my e raised to the power of integral p dx. That is achieved. So that's going to be 1 over x times root of 1 negative x squared, and this has to be multiplied by dx. So we will have to simplify and get the output. So now I'm going to take a out, it's constant, so let me retain x cubed there. I take x out, so it's going to be 1 negative x squared. I have a x here, so this is going to be root of 1 negative x squared. Of course there is a dx here. Now I can clearly take down this x with this, so that's going to give me a times integral x squared times. Now what is this? This is actually a x, and in fact I got a one more x. I can cancel this x, and this is going to give me x, so x times dx, so just one x there. Okay, that's fine. Now coming back, so what is this? If this is x and this is root of x, what is this? This is x raised to the power of 1 positive 1 over 2, which is nothing but x raised to the power of 3 over 2, right? So that is exactly what we've got. So this is going to be 1 negative x squared raised to the power of 3 over 2. Now we can bring it to the numerator and we can evaluate it, or we can just evaluate it from here. So what I'm going to do, I'm going to use substitution. So I'm going to say let 1 negative x squared. Now this is okay, let me just take it as 1 negative x squared. Let 1 negative x squared be equal to some t squared. So when I differentiate, I get negative 2 times x dx is equal to 2 times dt. So clearly the 2 can be cancelled. So this is going to give me negative x times dx is equal to t times dt. So if I were to replace that, x times dx is going to be negative t times dt divided by 1 negative x squared is t squared. So it's going to be t squared raised to the power of 3 over 2. Right? 3 over 2. So what happens here? This 2 and this 2 gets cancelled. So I know I have negative a times integral t dt divided by t raised to the power of 3. So I can get rid of this t with the t cube there. So that means this is going to be equal to a times integral dt divided by t squared. So it's all rough side. So I can push this up. So that's going to be negative a times t raised to the power of negative 2 times dt. If I were to integrate that, I get negative 2 positive 1 divided by negative 2 positive 1, which is negative a times t raised to the power of negative 1 divided by negative 1, which can be made to be as positive, positive, positive. So it's going to be a over t. But my t is what? T is going to be root of this, right? So it's going to be a times root of 1 negative x squared. What is all this? This is nothing but my q times, integral of q times e raised to the power of integral p dx. So this is what we have got. So now we got to take this and substitute it here and then give the solution. So let's do that. Now it's time for us to get the solution. So what is the solution? We started with z, right? Z times e raised the integrating factor. I'll just write it like this. Integrating factor is equal to this quantity q, right? Integral q times e raised to the power of integral p dx times dx. We have got this value, so that's going to be over here. So a over root of 1 negative x squared. Of course we need to place the arbitrary constant, but now it's time for us to make the substitution. So let me use this space that I can see here. Now z is actually taken to be as y cubed, so I'm going to revert it back, reverse engineering. And the integrating factor is what? Integrating factor is going to be x, substitute x times root of 1 negative x squared. So that's going to be the case, is equal to a over root of 1 negative x squared positive c. Now what we can do is we can cross multiply all these things. Now if I were to cross multiply all these things, what happens? This and this will get cancelled, giving me x. So let me use the space here. So I'm using the space here. So that means I get y cubed is equal to a times x, because of the fact that I got a root of 1 negative x squared and a root of 1 negative x squared. Both of them gets cancelled, leaving me with x, positive c times, c has got the denominator 1. So that would mean the entire term will be present here. It's going to be x times root of 1 negative x squared. So this is our final solution for this beautiful question. Thank you, students. Students, we are given this question: 1 positive y squared times dx is equal to tan inverse of y negative x times dy. Clearly this is not a linear differential equation that we've been exposed to. So where is the catch? The catch is, first and foremost thing, let us try to find, or in other words, let us try to write this system in dx over dy form. Probably if we were to able to do that, then some insights might arise. So that is what we are going to do. So I'm going to divide by dy. So if I were to do that, I'm going to get 1 positive y squared times dx over dy is equal to tan inverse of y negative x, because if I were to divide by dy, this is going to get lost, or in other words, this is going to get neutralized. Now what I wish to do, I would like to move this x to this end, to the left hand side. So this is going to be 1 positive y squared times dx over dy positive x is equal to tan inverse of y. Now this is something similar to what we have seen, but still not yet what we really needed. Now I'm going to divide by 1 positive y squared throughout. So if I were to do it, I'm going to get dx over dy positive x times 1 over 1 positive y squared is equal to tan inverse of y divided by 1 positive y squared. Now the form that we know, the form of linear differential equation, which we called it as a standard form, is actually dy over dx positive p times y is equal to q. Now do you see anything? In this case, we got an x here, and then we got a q present over here. So my p and my q are not functions of x. It's totally changed in this case. So we have to write that. We are looking at a system which is of the form, when I say I'm talking about LDE, linear differential equation, which is of the form dx over dy positive p times x is equal to q, where my p and q are functions of not x but y, right? So the integrating factor will be e raised to the power of not integral p dx but integral p dy, right? And my solution, it's not going to start with y, it's going to be starting with x. So x times e raised to the power of integral p dy is equal to integral q times e raised to the power of integral p dy times, it's not dx, it's going to be dy positive c. So this is what we are looking for, and we will have to achieve this. In getting that done, so I need a new page, so I will work the things over here. So now I need to obtain, consider integral p dy. So what is my p? My p in this case is going to be 1 over 1 positive y squared times dy. So if you were to integrate this, this is going to give me tan inverse of y. So therefore the integrating factor, which is e raised to the power of, not p dx, is going to be p dy, is going to be e raised to the power of, integral p dy is going to be tan inverse of y, tan inverse of y. So this is my integrating factor. So we have got that. Now let us now consider integral q times e raised to the power of integral p dy, which is nothing but integral. My q is tan inverse of y divided by 1 positive y squared. My e raised to the power of integral p dy is going to be e raised to the power of tan inverse of y. So we will have to substitute that. So let me just substitute like this. So it's going to be e raised to the power of tan inverse of y times dy. Right? I need to give the integrating factor there. So now the question comes, how are we going to integrate? So what I wish to do is, I will just say let tan inverse of y be equal to some t, and I differentiate that, I get dy divided by 1 positive y squared is equal to dt. So this is going to be integral tan inverse of y is t, tan inverse of y is t, and dy over 1 positive y squared is going to be dt. So this is what I've got, right? So now we can use UV technique. So if I were to use UV negative VDU form, okay, I can rewrite this with this form. This is going to be t times e raised to the power of t negative integral 1 times e raised to the power of t times dt. Okay, you can try this out. This will work out in the same fashion. So now I need to make the substitution. So this is going to be, my t is tan inverse of y times e raised to the power of tan inverse of y negative integral e raised to the power of t. This is going to be e power t. Of course, positive constant c is there. So this is going to be e raised to the power of tan inverse of y. Of course, there is a tan inverse of y that has to be placed here. So followed by negative e raised to the power of tan inverse of y. Now I can take e raised to the power of tan inverse of y out. So that's going to give me tan inverse of y negative 1 positive constant c. So this is what I have got for my q. Integral q times e raised to the power of integral p dy. So therefore the solution, we need to write the solution, right? So what is the solution? We started with x times e raised to the power of integral p dy is equal to q times e raised to the power of integral p dy positive constant c. Now I will write the right hand side, which is nothing but e raised to the power of tan inverse of y times tan inverse of y negative 1 positive arbitrary constant c. For the left hand side, x times e raised to the power of integral p dy. So we need to have the integrating factor, which is this, right? So substitute that. So x times e raised to the power of tan inverse of y. All I'm doing is just substituting it. Now if you want, you can simplify, but I think this is the right place to stop. Now if you want, you can divide throughout by e raised to the power of tan inverse of y. Now if you were to do that, you will get x is equal to tan inverse of y negative 1 positive. You are actually dividing, right, by e raised to the power of tan inverse of y. So this is going to give me c times e raised to the power of negative tan inverse of y. So this will be my final solution to the question. Thank you, students. I hope you enjoyed today's class, and if you like to see more content on university level mathematics, college level mathematics, engineering mathematics, competitive mathematics, math olympiad, and other math related topics, I would request you all to subscribe. Thank you and enjoy your day. Bye bye.